So our first speaker today is Tim Blackmore from the Infineon Technologies Limited. Tim is a senior principal verification engineer at Infineon. He's going to speak about decoupling, generation and simulation and an IP test bench. As I mentioned, Tim is a senior principal verification engineer. He's based in Infineon Technologies in Bristol, and his research focus is improving the efficiency of the verification of complex IPs, subsystems and SoCs, including the use of machine learning in that verification strategy. He is a global verification manager for Infineon's current family of Aurix 3G microcontrollers and is a visiting industrial fellow at the University of Bristol. So over to you. Thank you, Tim.
Thanks, Mike. Yeah, okay. So I get started straight away then. Okay, what I will do is get a pointer. Okay, so yeah, Mike. So as you said, I'm going to talk about having an IP test bench where the generation and the simulation are decoupled. So mostly the generation and the simulation would be closely coupled in an IP test bench. And this means that after the simulation completes, there's little remaining of the stimuli that have been applied to the design. So you might have a test and a seed, some coverage, but little else. I discussed the benefits of taking a decoupled approach, and just to be clear, so by decoupling here, what I mean is that the randomization of the test case is moved to a separate generator, and that the test cases are stored outside of the test bench. So, so I don't mean that test bench is sort of cleaved in two, but the randomization is separated and the test cases are stored. So first of all, I'll just go into a bit more detail about what decoupling means. So this is what a standard closely coupled IP test bench may look like. You have sequences which generate transactions in a constrained random manner. The transactions are passed on to the driver somehow, and then the driver drives them onto your DUT. The DUT may give some responses, and these responses may be passed back to the sequences to impact the generation somehow. There's lots of other stuff that goes on in the test bench, monitoring of the design behavior, checking the design behavior, and coverage. I won't focus at all on these because these things remain largely unchanged in the decoupling process I'm going to talk about. So I'll start with what the generation looks like in this alternative test bench architecture. So the point really is that the generation inside these sequences is moved to a generator, and the generator produces a test, and this test contains enough information to deterministically generate a test case. So it contains information like how the DUT is configured and the transactions that should be driven to the DUT. It may contain timing information, so it may determine the simulation time in which transactions are driven, or these may be driven based on synchronization events taken from the DUT. It may be necessary to embed a reference model inside the generator. So, for instance, if you're generating based on responses from the DUT, you would want to generate based on responses from the reference model. Although if you've just got very simple reactive sequences, you can just pre-generate. So for instance, if you just want to check, if you just want to generate a transaction to read a status register or something, if you see an exception, then you can just pre-generate such transactions without the need for a reference model to tell you that the exception has happened. So, so we move on to the simulation part the alternative test bench. So now the test is read in by the simulation environment. I've still got sequences here, but these sequences aren't doing any randomization. They've got I bordered them in yellow to show that they're different from the sequences in the original test bench, in the standard closely coupled test bench. So these sequences are reading in the test and changing them and changing the test intent into transactions, which will similarly be sent to a driver and sent onwards to the DUT. So this is the sort of the vanilla case where there's no simulation, where there's no randomization at all in the simulation environment. This can be tailored slightly to allow some minimal level of randomization in the simulation environment and retain most of the benefits that I'm going to talk about shortly. So the simulation environment may be allowed to generate a small part of the transaction, such as number of delay cycles, something like that. The simulation environment may be allowed to generate simple transactions on some simple interfaces into the design. If these modifications are allowed in the simulation environment, the stored test can be modified during simulation so that exactly the same test case can be replayed. So this is this very faint line coming from the simulation environment back to the test here. So some small modifications of the test may be allowed so that same test can be replayed in exactly the same way later on. So that was a bit of detail, but essentially what we have is we have a generator which generates a test. The test is somehow stored as a file or in a database or something, and then the stored test is retrieved during simulation and passed to the simulation environment. So this is what the decoupled environment looks like. So now I move on to some of the benefits of using such an environment. So the first one, and the reason we initially introduced such environments was to improve random stability. So with the standard approach, with the closely coupled approach, changes to generation constraints mean that test cases can be generated very differently. So typically there are complex dependencies between the constraints, and a change to a constraint somewhere across this line of dependencies leads to non-localized changes across the test case. And these kind of changes can happen anytime during a project. So for instance, you may generate cases which result in failures which are deemed to not be of interest, and this may result in a tightening of the specification. So that this can happen even as the verification progresses. And what we observed is, as this was happening, the test cases that we'd saved off to our golden regression, which we wanted to use to achieve our coverage, the test cases were changing. They were being generated differently as the constraints were changing, and because they were being generated differently, the coverage they achieved was different, and typically it was lower. So the graph at the bottom here was behavior which we observed on a real project. So during the first part of the project, the coverage wasn't progressing as we expected, and the analysis said it led us to the fact it was exactly due to random instability, and the projection was that we weren't going to close coverage on schedule. So we took the decision to move to a decoupled environment. Spent a few weeks implementing this decoupled environment, and as you can see, this actually brought the coverage back onto track, so that we could finish on schedule. So as well as coverage changing test cases which have generated interesting cases that have found bugs in the design can also change cross changes to the constraints, and it can be difficult to replay these interesting test cases if the design in the test bench have moved on. Of course, with the decoupled approach, you don't have this problem. The safe test cases just stay the same. So another benefit we've realized with this approach is that you can post-process the generated tests. So they exist in a file or in a database, and they can be post-processed. So for instance, where there are specification updates, you can change the tests to account for the specification updates, and in contrast to the closely coupled approach, these changes are localized. They don't impact the rest of the test case. Something else we've done is use machine learning techniques to identify interest in tests, and or tests which seem interesting or potentially interesting, and we only simulate these tests. So we don't simulate all the tests we generate. We simulate the tests which are of most interest, and this I presented back in DVClub in February, and we showed evidence that we could potentially save around 60% of our simulation time using this approach. So post-processing of generated tests is another benefit. Another benefit is regeneration and pre-generation. So the generator can be constructed to allow tests to be fed back in, and this makes it very easy to know if a test is still legal according to the as the generator changes. So if the test is not still legal, you simply get a contradiction, and this is very easy to debug, much easier to debug than some obscure simulation failure. So this is another nice side benefit of having this approach. And similarly, you don't have to feed a full test back into the generator. You can feed a partial test back into the generator and generate a full legal test based on this partial test. So I think Reese will talk about this more in detail later. Some other possible benefits is you can have mixed languages. So your generation and your simulation environments can be in different languages very easily. So for instance, generation environment could be in Specman, in E, simulation environment in System Verilog. You could have generation environment in Python. If you had a constraint solver, if you had a Python constraint solver, or whatever you like. Your generation environment could be in PSS, would be another example, which brings us on to another benefit, which is portability. So the tests which exist offline can be ported to other environments. This is something we've done in the past. It's kind of a lightweight PSS. You don't get all the power of a full PSS solution, but it is something we've used in the past. One other potential benefit I mentioned here is it allows for look-ahead generation. So you can try out a generated transaction on a reference model before committing it to a test. So as long as you can revert the reference model back to a previous state, then you can start to explore where your generation is going and whether it's going to take you into an area of interest before actually committing the generated transactions to a test. So those are a list of potential benefits you can derive from this sort of environment. So question, maybe an obvious question is, well, why don't we do this all the time? Why isn't this the default way of doing things? And to be honest, I don't have a really good answer to this question. People mention interactive generation as a reason for not doing this. So a need for cycle accurate generation of test cases, where not only the timing when the transaction is driven depends on the design state, but also the actual generated values. Typically, when I discuss this with people and they come up with examples, the examples may be aren't very compelling. So this may be the case, this may be needed, but my experience is that in reality this is rarely, if ever, needed. So I guess the main reason for not using this approach is just that it's non-standard, and you don't envisage any of the benefits applying to you. Okay, so that's the end of the presentation. Mike's open for questions now. Thank you very much, everyone, for listening.
Thanks, Tim. Let's, yeah, we do have a number of questions, so I'll run through the questions for you. Thank you. So I think we'll go to Sandeep first, because the first question I think you've answered now. So the question from Sandeep is, what is the interface between the test and the simulation environment? I guess what sort of asking what format that test is in.
Yeah, so it can be anything you like, really. It just text. You can choose whatever format's convenient for you. It's I mean it's certainly useful if it's readable. So for instance, if we come to this benefit, then having a partial test which is readable and reviewable is certainly useful.
Okay.
But text is a standard format we use. Yeah.
Okay, and I guess looking at your diagram there, it's about using the virtual sequencer. So it's a sort of inputs to that virtual sequencer that you've got inside your test. Is that correct?
Yeah. So your environment will interpret your test to generate these transactions. Yeah.
Okay, and then I guess what you're saying
So a very simple example is if you want to if you want to configure a particular register to have a particular value, you can just put the register name and value in your test, and then you will generate a transaction which writes that value into the register inside the design.
Okay, and then another question is how much randomization would you then leave into the simulation environment? How much would you put into the test generator? Is there guidelines for that?
So I would put as little as possible in the simulation environment. I would only put randomization in the simulation environment if it was really necessary.
Okay. So I think the example you gave was on delays. So that's a good thing to put in the environment rather than into the test generator.
Yeah, but maybe not. Maybe using synchronization events in the test may be a better way of doing this. Just yeah. But if somehow you want, yeah, it's hard to think of a case. But if you want your timing to really depend on a DUT state, which isn't easily decodable as a synchronization event, I don't know, then maybe you'd want to put the time in, determine the timing in the simulation environment.
Okay, and then a question on the reuse. So have you done this with horizontal reuse, so IP to between IP versions, and vertical reuse, so IP to subsequence to SoC?
Yes, yeah, definitely, yeah. So the post processing, for instance, allows you to horizontal reuse.
Yeah.
And we've used it vertically on porting tests up to SoC and even onto FPGAs and post silicon environments. Yeah.
Okay, and I guess the moving a test from to post silicon and FPGA, this becomes much easier because you really do want to separate out the test from the test bench.
Yes, it's a natural way of doing anything at those levels anyway. Yeah.
Yeah. Okay. And We've got a couple of minutes left. So one final question, a bit on the machine learning. How is machine learning used to get rid of, get a list of required tests?
Okay, so I guess, Mike, this presentation is available online anyway. So there's certainly more detail here, but we use machine learning to determine novelty of a test. So we'll look across the generated tests and choose the ones that look most novel with regard to the tests that have already been simulated, and then pass those tests onto the simulation environment. So I think one observation there is our generation is very quick. Our generation just takes seconds, yes. and the simulation is relatively long. So any simulation time we save is real save in terms of schedule.
Yeah, and also presumably your AI requires fast generation time to learn.
Yeah. Okay. Yeah. You want to feed it a reasonable number of tests. Yeah, for it to do something interesting. Yeah.
Okay. And the last question is: can we reproduce the failing test with the same seed?
So the idea of seeds becomes rather redundant here, because you actually have a sort of physical test.
Yeah.
Here. So that might be a counterpoint to this difficult to reproduce errors, because you can go back to an earlier version of the test bench and use the same seed. But if in the process of fixing the bug, or if there's been a change to the design interface, concurrently, then that's maybe not going to work. So it's not always a reliable way of reproducing errors to move to an earlier version of the test bench and generate them with the same seed.
Okay. Thanks, Tim. There are another couple of questions, but maybe we can ask them after this. I'm just aware of the time. And a big thank you to Tim. Thank you very much.